So let's go now for the next 5 speakers. And the next one is going to be Luca Martulli from KULeuven in Belgium. Luca originates from Italy, where he graduated in mechanical engineering, and he's one of the Marie Curie Fellow of the Fibre Mode project, a European project which aims at the development of new failure prediction methods for composites. And so the title of his talk today is Automotive Components Made of Carbon Fiber Sheet Moulding Compound, Design, Manufacturing, and Properties. Luca, come on.
Thank you.
Great. Are you ready, Luca?
Yes, I am.
So 3, 2, 1.
For aerospace companies, the transition from metal to composites was almost natural. They need strong, light, and large parts for something like hundreds of aircraft a year. But me, I work for both KULeuven and Toyota, and we need to make millions of Yaris or Prius per year. For automotive needs, strand-based composites like sheet molding compounds, or SMCs, are the answer. These are composites in which chopped carbon fiber strands are mixed with thermoset resin to form prepreg sheets. The compression molding process makes SMC the best compromise between the processability of short fiber composites and the high mechanical performance of continuous composites. And yet, if you bring your car to the repair shop, maybe get to see some parts, they're almost still all gray, shiny, and metallic, instead of having that very cool look of black marble that is typical of SMC. Truth is, SMC are mainly used for thin panels, despite their huge potential of application to structural components, like this one. This is a prototype chassis part I manufactured and tested during my PhD. Now, I can assure you this is very light, but I'm still going to put it down. So why aren't our cars filled with SMCs? The answer is that we still don't have good models to predict the properties of SMC, and this means we engineers cannot design SMC parts effectively. These models have at least one of those 3 defects. They're developed either for short fiber composites, which clearly have a different microstructure. They're empirical, which means you need money and time for testing. And some of them even miss the link with the manufacturing process. Now, why is that important? Take a look at the graphs you see there. The first one, the one on the left, is relative to some tensile tests I did. So strand orientation in SMC is determined during the compression molding phase. And using that, I was able to manufacture specimens having strand orientation of 0 or 90 degrees. There's quite a difference there. And it gets even worse when going to part production. I manufactured my component using 4 different charge patterns, meaning 4 different ways of placing the prepregs inside the molds. During testing, the bending strength of the part varied by 200%. To increase engineers' prediction capabilities and thus spread the use of SMC, we're developing the simulation chain you see here on the left. First, we run compression molding simulations to evaluate microstructural features of our virtual components, like strand orientation or defects. Then we developed 3D models that predict local values of stiffness and strength, using only mechanical and geometrical properties of the constituents. This means that the models are developed for strand-based composites and are based on mechanical theories. This is very important. Models based on tests require money, time, and are valid only for the material system you are testing. You change resin, you need new tests. You change fibers, maybe even just the length or the volume fraction. You need new tests. With theoretical models, you have curves describing how each of those parameters affect the final properties. And this is done within hours, sometimes even minutes or seconds. The chain finally ends with a structural simulation. Notice that the arrow continues there. Why? Well, thanks to the first step, molding conditions and mechanical performance are now linked. This means that the chain enables us to evaluate not only the best design, but also the best molding condition for each component. Optimizing the molding condition of my part required 8 weeks of trial and error procedure involving both molding at 150 degrees and testing. With the simulation tool we're developing, this could be done faster, cheaper, and most importantly of all, comfortably sitting at your desk at 20 degrees. So let me conclude with a key message here. We're now in an era in which no matter how astonishing a material is, we cannot use it in our structures or vehicles if we're not able to simulate its behavior effectively. My job is to make this possible for carbon fiber sheet molding compounds. Thank you.
Bravo, Luca. Thank you very much for an excellent talk. Don't forget that. Slightly less dramatic exit, I suppose.